So the first question asks us to determine a scale. What I would do there is measure the length of this vector right here with a ruler. That's difficult to show on the screen, but when I do it, I get 4.6 centimeters. Now, if you're doing this with the axial Regents question, you might get a different answer just because this one has been scaled to fit. But what I would do is I would take that 4.6 centimeters and say 9.4 newtons must be the same as 4.6 centimeters. Divide to get centimeters by itself. 9.4, do this up here, 9.4 divided by 4.6 gives you right about, or close to 2.0 newtons. It's actually 2.04, I think. Yeah, 2.04 newtons. So scale 1 centimeter is going to be equal to 2 newtons. And the next question asks us to use that scale and actually add these two vectors over here on the right. Now, real quick before we draw it for real, when you add these two vectors, the resultant is going to be somewhere between these two. So if this is going this way, this is going this way, it's going to be something like this. Now, there's two methods. One method is what's known as the parallelogram method, and which would mean you go from the beginning to here, draw this, and that will be your resultant. The other method would be to take this vector and actually move it to here. This is called the head to tail method. And either way, you're going to get the same answer. But we have to get the scale right, and we have to get the directions exactly right. So what I'm going to do is I'm going to move this vector A over to B. Now, to do that, we're going to have to try using a protractor. Now, because I can't show you a real protractor, I'm going to try to drag this picture of a protractor here to show you. Remember, this is always going to be the 0 direction, 90, 180, etc. So when you bring the protractor here, put it like that, and then when you read this with yours, which will be a little better, I'm getting 25 degrees. So this is the 25-degree direction. So when I go to the head of the first vector, I put it there about like that. What I'm going to have to do is I'm going to have to put a little dot here, and at 25 degrees, and we're going to use that to give us our direction. So 25 degrees is about, I'm using a bigger protractor here. So what I did is I put a little dot over here to give us the overall 25-degree direction. And I'm going to use a ruler in that direction. But before I do that, I need to measure this vector, which is 2.8 centimeters long. So what I'm going to do is when I go to redraw it, I'm going to make that also 2.8 centimeters. So I put my protractor, or not my protractor, my ruler across here, and I'm going to go 2.8, draw an arrow. Now the resultant is going to go from where you started to where you end up. So we started here, head, tail, and we ended up here. This is going to be the resultant vector, the R. Now when you have these vectors, there are two things you can always tell about them. One is the magnitude, the other is the direction. This question didn't ask for the direction, but when I put my protractor up to it, I got about 112 degrees. What it did ask for was the magnitude. So to get that, what you have to do is you have to measure this. And when I measure this, I got 3.4 centimeters. So now what we're going to do is we're going to take that 3.4 centimeters and we're going to use our scale, which we found earlier, of every 1 centimeter is equal to 2 newtons, which is going to give us 6.8 newtons for the magnitude of the force. Now let's look at the other question on this page, which is about a jet that's slowing down. So the jet is here, it's heading in the north direction, and it's slowing down. So this is going to be our acceleration, which is going to be negative because you're slowing down. This is going to be its initial velocity. Notice it has a direction, north. This is going to be VI. And because it comes to rest, that's sort of a code word for telling us that the final velocity is going to be 0 meters per second. So once again, if I was to sort of draw, I like to have an expression. If you want to see the big picture, you have to draw the big picture. Namely, you have to show where the initial and the final positions are, because that'll help you keep everything straight. So writing out variables, we have an initial velocity that is 70 meters per second. We have a final velocity that's 0 because it's stopping. We have an acceleration that is -2 meters per second squared. And what we want to know is we want to know what is that displacement? How much runway does it take this jet to stop? So we have to look at our reference table to see which equation is going to work for us. And the way we pick that is we pick an equation that has the thing we're looking for. In this case, D, and we have to know everything else that's in that equation. So looking at your reference table, in this case, the equation that has a D in it, and we know everything else, is this one. Because we know the A, we know the VI, we know the VF. This is the one where we don't need to know time, so that's the one we're going to use. So VF squared equals VI squared plus 2AD. VF is 0. It's a good idea to get in the habit of, even though it's 0, plugging it in with the units. VI is 70 meters per second squared plus 2 times the A, -2 meters per second squared, times the displacement. So you bring that over, that's going to give you -4,900 equals -4D. By the way, notice you don't have to have units at this point. And you're going to solve for the D. The D here is going to be 1,225 meters. And then the last question says to draw using a scale of 1 centimeter equals 0.5 meters per second squared, an arrow representing the acceleration. So we have to take that acceleration, that 2 meters per second squared, and we have to convert that to centimeters used to represent that. So 2 meters per second squared times every 1 centimeter is 0.5 meters per second squared. That's going to give you an arrow that has to be 4 centimeters long. And because the jet is traveling north and it's slowing down, that is going to be going south. And this will be 4 centimeters long. There's not actually enough room on your paper to draw that, but that's what it would be.